All right. Hi, everyone. Thanks for joining us today. We'll be starting the webinar in just a few moments. My name is Tina Fabiano, and I'm on the enDAQ Marketing and Engagement team. In a minute, Steve Hanley, our Vice President of Product, will be presenting today's webinar and Q&A session on the top 12 vibration metrics to monitor and how to calculate them. Vibration signals are complicated, and the more you have to monitor, the more complicated it gets. In this webinar, Steve will demonstrate how to quantify vibration signals into a handful of metrics that can be tracked and compared easily. He'll go over 12 metrics, including acceleration peak, acceleration RMS, velocity RMS, displacement RMS, peak pseudovelocity, and more. And he will explain how each metric is calculated and what it is most helpful for. We've generated a lot of interactive plots for this webinar using Plotly. I'll share the link in the chat box to this presentation so you can follow along with Steve and check out the plots as he explains each metric. We hope that the interactivity enhances this webinar for you and gives you even better insight into this topic. This is a 40-minute session. As you're watching the webinar, don't hesitate to use the chat feature or the Q&A button to ask questions. Steve will try to answer a few questions as they come in, and then he'll answer any other questions during the Q&A portion. We'll also have a few polls throughout the webinar for you to answer. We're really excited to be presenting the top 12 vibration metrics to monitor and how to calculate them to you today. We hope you find this webinar informative and that you leave with a better understanding of how to analyze the trends of these metrics. So with all that, I'm happy to introduce Steve Hanley, who'll be taking it from here.
Thank you, Tina. Let me share my screen. As she just said, she's going to be texting out the link of this webpage, and I'm really excited. She did a great job with the team to build this out. So it's a different format than what you're maybe used to with the webinar. We built a web page that you can, that we're going to share with you now, so you can follow along as we go. And I don't know about you, but I love learning by doing. So hopefully this will help you really comprehend the data and the information we're sharing. This also lets us have interactive plots in the web page, which is really fun, and it's generated with Plotly. It's something that I've fallen in love with since I found it a couple of years ago, and we're looking to implement it in our cloud software as well in the next month. So I love Plotly, and hopefully you guys love the format of this webinar. So what are we talking about today? Well, we're talking about how to quantify vibration signals into a handful of different metrics. Vibration signals are complex, and so it's one thing to look at the complex signal in the time domain or frequency domain if you have one or maybe two vibration profiles. And once you have a lot of them, you need to quantify it into a handful of metrics and compare those metrics. And this is especially true if you're looking to monitor something over time, like the health of a system. So what's the data we're going to look at today? This is data generated from Case Western University. This is their website that they share the data. They had a bearing and they had a variety of different accelerometers in this assembly, and they introduced a series of fault conditions and recorded that data. So there's a lot more than the 4 signals here, but we're looking at these 4 signals: the normal bearing, and then these 3 fault conditions. These particular ones we're looking at were when they machined a small hole into the inner race of a bearing. And so fault 007, 007, that's kind of cool name. It is a 7 mil diameter hole that they machined. And then fault 014 is a 14 mil, 1,000th of an inch hole that was machined into the bearing. So that's the data. Let's get into it. Well, actually, before we get into it, let me share a poll question to get everyone's blood flowing a little bit. I'm just going to ask you here, when you do vibration testing, are you typically looking at 1 to 3 or 4 different signals at a time, or are you trying to monitor something over a long period of time? And that's the first poll question. See if you guys are, what the difference here. It looks like a lot of you answering this are looking to monitor, although now it looks like it's maybe a little more split. So I'll share the results in a second. Okay. Yes, this is great. It's pretty split between people monitoring over a long period of time, many different sources, as well as just comparing a handful of different vibration profiles. Everything we're going to go through today should address both those applications. So here's the bearing data. Again, this is an interactive plot. You can zoom around. You can isolate one of the signals by just double clicking it, or turn off a signal. And so here's the normal bearing and the 3 faults. And looking in the time domain, how would you quantify this? The first thing people do is they look at the peak. What is my peak acceleration? And we'll see here that sometimes that can be a little misleading. But looking at the peak, you can tell, the normal bearing has a peak around 0.2 Gs. That first fault condition has a peak maybe 0.6 or so. That 14 mil bearing has a larger peak. It's actually over a G, 1.3 over here. And then this is where it gets a bit interesting. So the fault 21, it's a worse fault, it's a larger hole. It actually sees your acceleration peak less than the one with the smaller fault. It's about 1 G as opposed to 1.3. But when you compare these two signals, we look at kind of the broader profile, it does seem like that fault 21 on average or generally has higher levels, but there was some of that peakiness in the fault 014. So here are some of the first metrics you can look at just in the time domain. And so the acceleration peak, which I just showed you, and you notice that there's some trend with the peak values as the fault condition gets worse, but there's that a little bit of anomaly between the fault 14 and fault 21. And why is that? Well, when you look at peak acceleration, peak can be somewhat heavily influenced by random events. You can measure a transient thing that maybe only occurred once. It doesn't necessarily represent the full vibration profile. Then peak is also heavily influenced by sample rates and where the sampling lines up with where the peak occurs. So peaks can be misleading, but if you look at a variety of peak levels and kind of take an average of the peaks, that can be useful to get an idea of the peakiness of a signal, which is indicative of bearing health and other vibration profiles. So my caution, though, is just when you look at peak, don't look at the peak of just one signal. That could be misleading. You look at it as an average. And so if you're monitoring over time, take a moving average of your peaks. Now let's look at acceleration RMS, which would be kind of my favorite metric, combined with standard deviation, which I'll explain in a second. And you see acceleration RMS has a clear trend. As there's a fault condition, it has a higher RMS, and as that fault gets worse, the RMS increases. So this looks like a pretty good indicator of bearing health and the energy in a vibration profile. But we'll get to this a little deeper later on. We're going to look at acceleration RMS within certain frequency ranges. And then there's a crest factor. Crest factor is a unitless metric. It's just dividing the peak by the RMS value. And so it defines how peaky your signal is. So because it's tied to the peak, again, crest factor is a great thing to monitor. You see it's not really a perfect trend here, though. And so just be careful if you just look crest factor of a single file, you have to take that moving average of crest. Now, here's something that's pretty interesting, and I only really recently learned this about the standard deviation. Standard deviation values and the RMS values are pretty spot on, you can see. And it turns out, and we all know what standard deviation is, right, from statistics, and that's just monitoring or measuring, the population of a certain metric and how much it deviates. It turns out standard deviation is an AC coupled version of RMS. And so if you have a signal, you take the DC offset out, take the median out, mean value out, and then measure RMS off that, that will be the same thing as calculating standard deviation. Let me demonstrate that with some simple data here. This is a 1G 7 hertz profile that I just simulated. So it's a pretty easy vibration signal, and I sampled it at 100 hertz. And you see here, when you zoom in, this looks like a very clean, simple sine wave. But then I showed what happens if I sample it a little slower. If I'm sampling only at 29 hertz, and you see it kind of looks a little funny, you still see roughly that 1G 7 hertz signal, but it certainly looks a little different. And then if I sample even slower at 15 hertz, it still captures it, but it's getting pretty close to aliasing the signal. And then I also am looking at a 29 hertz sampled signal with a 1G bias. So this would be, if you had an accelerometer that measures gravity, this would be what it would have measured for that vibration signal. And now let's go down here and look at those same metrics that we looked at with the bearing, but on those 4 signals. Remember, those 4 signals are measuring the same thing. It's a 1G 7 hertz sine wave, but they just have a few different characteristics about how it's sampling it. When you're sampling fast enough, you know, 100 hertz, it measures the peak of 1.0 perfectly. And the RMS value is pretty close to what you'd expect, which would be 0.707 square root of 2/2. But when we're sampling a little slower, we can't quite get the peak. You know, the sample, the point at which we sample the data, it has to perfectly align with when it's at the crest of the sine wave, and it can't quite get there. And you know, this is pretty close. You see 0.999, and when you're sampling a little slower at 15 hertz, it's 0.995. It's still pretty damn close to 1. But I just wanted to demonstrate here, as you get a real vibration profile that's got a lot of different frequencies to it, that sampling rate can really matter in how well you're able to capture the peak. So keep that in mind. That's why it is hard sometimes when we just look at acceleration peak. We have to kind of look at an average of the peaks. And then, of course, if we had that 1G bias, you're going to measure the peak of 2Gs. And if we do the RMS on those signals, so the RMS, I should have mentioned, is root mean square. So you square your value, take the mean of it, and then take the square root of that. And the peak is pretty self-explanatory. You're just finding the max, although the only caveat there is you should do an absolute value first and then get the max. So you still can get a significant negative acceleration event as well. But now look at the standard deviation calculation. The standard deviation is exactly 0.707 for all of those signals, regardless of the sample rate, regardless of the DC offset. I only recently learned this. I thought this is pretty compelling. It basically is an RMS calculation for you. And for some people, I know they filled out the questions when I asked when you signed up, you know, and somebody said, we're interested in really memory efficient ways to calculate some of these metrics. And standard deviation is going to be an easy calculation. It's going to be built into most libraries you'll have access to, even embedded, and it's kind of doing the filtering for you. So I think that's a really good one to look at. It basically is RMS, and it's quantifying the intensity of a vibration signal. All right, while we're still in the time domain, we're going to do an integration. So, you know, a lot of people want to look at the velocity of a signal as well as the displacement. And velocity, I'll talk a little bit more about in a second. That's really the most important metric oftentimes in vibration testing, because that corresponds to energy of the vibration. Remember, 1/2 mv squared, velocity is what quantifies energy. So to look at how we integrate the data, I have that same 1G 7 hertz signal that I constructed, but now I'm going to look at a pure one as well as one that I added just some broadband noise. So you see it kind of has this peakiness all over the place, but it's still that at the core the same signal. And if I do an integration off that profile, I'm going to see something that I don't expect. It's basically not oscillating about 0. You'd think there's periods of time in this vibration where the system isn't moving, right, as the acceleration is changing. But when we go to take the integral, because it's starting at 0 G's acceleration, it's starting immediately with the velocity component that ramps up. And then it starts to come back down and gets to that point where the velocity is 0 again, but it never crossed 0, never became negative, when in reality, it's moving forward and backward. And so because we just kind of crudely started from the beginning and the end and took the integral of it, and by the integral, I mean, we're just doing a cumulative trapezoidal calculation, so just the area under the curve. You see the right amplitude, but now you have an offset, so a velocity that's oscillating about 7.5 inches per second, as opposed to a velocity oscillating at 0. So how you fix that is by applying a taper. And so what the taper does is and it's a Tukey window, is it forces the beginning and the end with a ramp to 0. So it starts and ends at 0, and then in the middle, it has the full profile. And this is really effective to give you what you'd expect here in this integration. The only downside is, in order for this to work, I have to apply the taper, which means I'm filtering out real data that was occurring in the beginning and the end of my signal. And so when I later calculate RMS off this velocity, I have to take that into account and not take the velocity RMS off the full signal because I applied that taper. I'm going to take the velocity RMS off the middle because that's where it's still true. So when you have a pure sine wave, in order to integrate it, you just need to apply a taper. But when you have a noisy sine wave, even if you apply the taper, it's still not looking like it's supposed to. And remember, most vibration profiles are going to be noisy in that there's going to be a lot of different frequency components. So you still need to do one more thing, and that's apply a high pass filter. The high pass filter is just removing kind of this slow, meaningless DC bias and really slow vibration. It's not even really a vibration, it's just an artifact of the integration. And when you're integrating, the lower frequency content matters more. And so we need to get rid of this lower frequency content that isn't real, like the DC offset and things that are kind of just an artifact of the sampling. So if you apply that high pass filter between your integration steps, as well as the taper, you can get what looks to be something that corresponds well with the pure sine wave. It's still a bit noisy because the noise is still there, and I just want to stress that when you apply this high pass filter, you aren't removing vibration that's significant. You're just removing I applied this at above 1 hertz, so you're just getting rid of that kind of stuff. So that's the integration for velocity, and I'll get to that in a second. So now if we integrate velocity again and we get to displacement, if we don't apply that taper, you just have a thing, because remember, if we don't apply the taper, that means the velocity is never negative. It's just oscillating above 0 the whole time, which would mean that the thing's running away. Over the course of 2 seconds, it moves 20 inches, which isn't true. Well, if we apply that taper, we get pretty close to what we'd expect, but still there's this, it doesn't look like it's supposed to as you'd expect. So again, once you apply that high pass filter as well, it removes a trend that is an artifact simply of the integrating step. And the noisy data also will look right with applying the filter as well as the taper between every integration step, as well as at the end of the integration. So now let's go back to our bearing data. And this is what surprised me a little bit. I expected that the faulty bearings were going to have higher velocity and displacement because I assumed there'd be more energy in those vibration profiles, but it turns out that's not true. The normal bearing has quite a bit more velocity than the 3 faults. And then when we're looking at the displacement, it's even more egregious. So why is that? Well, we'll see later on that the frequency content is very different between a normal and the healthy bearing, where the normal bearing has higher lower frequency content and lower higher frequency content. And we'll kind of demonstrate that in a moment. Now, I should have included a table of the inner velocity and displacement RMS, which I do later on, but I'll just highlight that velocity RMS tends to be what a lot of systems look at solely for quantifying vibration. And again, because that's related to energy, and there's an ISO standard that will define vibration severity based upon a velocity. Displacement RMS is something that's nice to look at because it's something that's pretty intuitively understood, but it's going to be pretty damn low in most vibrating systems. So it's only included because we can, but I'll talk about a little later too, is that displacement is helpful when you're looking at an imbalanced system. So it can be a good indicator of that. Okay, so that was time domain. Now let's get into the frequency domain. And so first, before we go back to the bearing, let's look at an FFT of a simple profile I'll build that just has 2 sine tones, one at 7 hertz, and now I added one at 13 hertz. And you see here what that looks like. It's pretty straightforward. And if we do an FFT of that, we get what we'd expect, right? You have a peak at 7 hertz at 1G, and another peak at 13 hertz, 1G, and everything else, every other frequency is 0. And this looks great. There's just that one peak. This is perfect. This is what you love to see at an FFT and what you expect to see. What happens if I do an FFT of something that doesn't have a complete integer number of cycles? So in this FFT, I did the full 10 seconds of data. And in those full 10 seconds, it completely finished an even number of cycles. So there was no revolution that was kind of cut short before it could finish. Whereas here, I'm doing 1.1 seconds, 5.5, and 10.5, which means I can't complete all my cycles. And so in the FFT is trying to reproduce that time domain data with a bunch of frequencies. If it has to reproduce something that hasn't finished a cycle, it's going to have to use other frequencies to do so. And so you get what's called leakage in other frequency ranges. And remember, this is the exact same signal. We're just doing the FFT of different periods of time. And that when I'm doing 1.1, you don't even see the peak at 13 exactly as you'd expect, which is part of the problem. And you don't see the peak at 1G. It kind of spills into these other frequencies. And it looks maybe a little better with the 10, but it still doesn't get to the peak at 1G. It gets pretty close to showing you that 6.996 hertz. So it's pretty damn good at telling you the frequency, but the amplitude is not going to be quite right. So how do we fix that? What's the solution for doing that? And that's the power spectral density. Power spectral densities are my favorite. Let me explain how they're calculated. A power spectral density actually looks at first a FFT, and it takes the square of the FFT. So it takes the FFT result, squares it, and then divides by the bin width. And what this does is a couple things. One is by dividing by the bin width, I've normalized it. So I can compare signals that are different lengths, sampled at different rates, and all that. It's really good. And we'll see later on in this webinar, in the PSD, I can integrate this to get RMS, because that's the one issue that people have with PSDs is they look at the units. G squared per hertz. What is that? You know, when you look in FFT, it's really easy to understand. That's just G. So what's G squared per hertz? Well, again, it's the FFT squared divided by the frequency bin width. And you'll notice, and I explained it in the blog, that if I were to take the integral under this curve and take the square root of it, that works out to 0.707. So that's the RMS. And so that's something that's really cool at PSDs, and I'll show later on, is that taking the integral under it and taking the square root of it gives you the RMS vibration, which lets you also specify different frequency ranges and get RMS within specific frequency ranges, which can be super valuable. Now, before we really focus on the PSD, I want to put the FFT to rest. This is now the FFT of the actual bearing data. And I'm looking at just one profile, but I have an FFT calculated off of the full 10 seconds and one off of just a 1/10 of a second. And you see here that the order of magnitude between these two FFTs is way different. And so if I were to compare these two signals, I'd say, oh, the blue line here is a worse vibration profile than the red line. But that's not true. It's the exact same profile. But if I look at the PSD, they match up perfectly. So PSDs are how you quantify a vibration signal in the frequency domain. And the PSD gives us a ton of other useful tricks, which I'll show in a second. So here's a PSD now of those 4 bearing profiles. The other nice thing of the PSD is you can specify the bin width. So the way you calculate it is you first actually segment the data into a series of different time ranges, get the FFT of all those different time ranges, average those FFTs together, then do the squared and then divide by the bin width. And so that lets us explicitly set the bin width that we want, basically the resolution in our PSD. I like doing a resolution of 1 hertz, and you see here, there's a peak around 30 hertz, which corresponds to the motor RPM of 1800 RPM. And we can pull off, when we have this PSD, where did the peak frequency occur? In the normal bearing, the peak frequency is around 90 hertz. The fault bearing has a peak around 1,000 hertz. That higher fault has a slightly higher peak of 3,200, and the even worse fault has a even slightly higher peak of 3,300, which is nice, and that might be indicative. We see there's a trend there, but there's a better way to quantify it. But that's something that we can pull out in the PSD when we have this high resolution of it, is say, oh, where is my peak frequency, and capture that. But I actually like to pull out the peak frequency for a few different ranges. For example, I may want to say, all right, where's my peak frequency from less than 100 hertz, and then where's my peak frequency in this range, from 100 to 1,000. Maybe pull off 2 or 3 peaks. So you can do that once you have the PSD. Now, in this view, it's still a little hard to compare the 4 signals. You can tell that the normal bearing has some other stuff going on at low frequencies and less at high frequencies, but it's a little hard, admittedly, to see it here. So what we can do is really cool and do this cumulative RMS calculation off the PSD. Again, you're just doing the area under the curve and taking the square root of it. And within this view, it's super easy to compare the normal bearing to those 3 faults, whereas you see that normal bearing has a ton of RMS vibration in the lower frequency ranges and very little difference once you get to the higher frequencies. And remember too, from earlier, here's my peak RMS. My cumulative RMS is 0.065 G for the normal bearing, 0.12, 0.16, and 0.2. That's pretty much exactly what we measured in the time domain. The other nice thing about the PSD is I can easily integrate for a velocity and displacement PSD. You do that by just multiplying by omega squared. Omega is 2 pi f. You do have to pay attention to units. We're going from G's, which is meters per second squared, to maybe inches per second or millimeters per second. And then there's a squared term. So you may have to take a special note of that, but it's really easy to integrate a PSD to velocity and a displacement PSD. And then once it's in that view, we again can get the RMS from the PSD. And so here I'm comparing the RMS calculated from the PSD for velocity versus that RMS I calculated when I just integrated the data in the time domain, and then do the same for the displacement. You see they correspond pretty well together. There's a bit of an anomaly going on, and that's likely because of some low frequency content that doesn't exist when we do the integration with some filtering and the taper and stuff, but does in the PSD. But in general, I think that's a nice thing. One of the nice things about PSDs, is a lot of nice things, is you can easily calculate and integrate the velocity and displacement straight from it. And remember, velocity RMS tends to be, for most applications, the way to quantify the energy of a vibration signal. And there's an ISO standard again for that. All right, let's go back to the PSD. And remember that first PSD I shared it was really noisy. Noisy isn't the right word, but I had a 1 hertz frequency range. So there's a lot of lines to show there. One of the nice things, again, about the PSD is I can define my frequency ranges, and I can define logarithmically spaced frequency ranges. So it looks great in this view, which a PSD tends to be plotted on a log-log scale. So I can do a log space frequency range, so it's evenly displayed here. And this is a 1/3 octave, which means every frequency point is 2 to the 1/3 greater than the previous one. Okay. And this is a standard one. You could do just 1/1 octave, which means every frequency is an order of 2 greater than the last one. So what's nice about this is I can reduce my PSD up here that has 6,000 data points down to maybe as little as 10 in a 1/1 octave. And then when I have that simple of a PSD, I can input that to a shaker system very easily. I can type out the 10 lines. Some shaker systems will let you import the full, the full 4,000 points, but it's not needed. You can do a simpler one by looking at the octave. Now, if we want to get even more granular, we can do that again with the PSD and just calculate the RMS within certain frequency ranges, which is what I did here. And sorry, I'm going to have to take a sip of water. I've been talking. Okay, so I'm looking at these three frequency ranges that are chosen for a reason, and this is kind of an industry standard. So 1 to 65 hertz, low frequency range, that tends to be dominated by the boundary conditions, and specifically the vibration that's from the motor or something else in the system, not necessarily the health of the inside of my system that I'm measuring. And so our vibrations in that lower frequency range tend not to matter too much about the health of my subsystem. The exception is when you're worried about imbalance. If you have an imbalance in your system, you'll see it in the low frequency range. Just like I mentioned earlier, you'd see it in the displacement. Because remember, when we're integrating, lower frequency content becomes more and more important. So when you double integrate, you're basically only looking at the frequency range less than 65 hertz or so. And then that middle frequency range, 65 to 300 hertz, is also tends to be dominated by boundary condition type stuff like looseness or misalignment. And so if you're worried about those things, if you see the vibration, the RMS change in that frequency range, that tends to be your fault, is something's misaligned, something's loose. It's not necessarily broken, but so it's a really easy fix. Just like the other one, if you see a ton of low frequency content, something's not balanced, it's not broken, which is good, you can easily fix it, but it's not, but the higher frequency content, that tells us something inside our system is bad. And we see this is, kind of the perfect representation of the fault. You see a really low frequency RMS from the normal bearing, and then a big jump for the fault condition, and then the RMS gets greater for those other fault conditions. So for our particular application, this RMS in the high frequency range from 300 hertz is what I would track over time to indicate the health of my system. Now, before I summarize all the metrics, I want to show the shock response spectrum. This tends to be used, as the name implied, for shock, but a lot of vibration systems that we're measuring have transient events, so it could still be helpful here to look at the shock response spectrum. I'm looking specifically at pseudo velocity, and so this is the pseudo velocity of a system, how it responds to the given vibration input or shock input for a series of different natural frequencies. And so this is quantifying the worst case velocity that the system would respond with, which, just like velocity RMS, the worst case pseudo velocity response is quantifying the damage potential in a system. So I want to see where's my peak and what is my damage potential of this vibration profile. This is very low. You see the peaks around 1 inches per second. You worry about stuff in the 100 roughly inches per second range. So we're not going to get damage from that perspective here, but it can still be helpful to see, to kind of quantify a vibration profile. The other thing we can do in the shock spectrum here is find the peak, and there is actually a decent trend here of where these peaks occur, just like we saw in the PSD with the different fault conditions. So here's a summary of all our metrics. Again, we started by looking at the RMS, and we saw there was a good trend here, but an even greater trend occurs when we look at just the high frequency content. And that's because there was a lot of RMS energy for the normal bearing that it was kind of misleading and not really indicative of damage. And so if we just look at the high frequency content, for this particular application, that is the thing that corresponds most to damage. But again, that's just this particular application. I'd encourage you to start with all these metrics, play around with different frequency ranges as well. And you'll have to kind of play around with that by looking at the PSD and kind of get an idea of which frequency range matter. But ideally, you pick a certain frequency range and the RMS within a certain frequency range to track. And that would be most likely the best way to track the vibration health of a system. But you have to start by doing a bit of exploration. And so to conclude this, and then I know we have a bunch of questions, the first thing, in order to reproduce any of this, you have to go get some data. So we have, of course, some vibration sensors you can buy and use. They're super convenient, easy to use, but there's other accelerometer and monitoring systems out there. So you have to go get data, and then you have to summarize those into quantifiable metrics. The blog that we reference here that I wrote gives you those equations of how to calculate that. It also shares native Python code, exactly how I calculate all these things off the bearing data that you can use. And we're going to be publishing that Python code as a library, so it can make it a little easier. It's just a simple function you have to call. And I know a lot of you don't use Python, so I'm going to ask my final poll question, which is, how do you calculate and analyze your vibration data? And so I know a lot of you don't necessarily use Python. A lot of you are MATLAB lovers, which is great. So one thing we're going to do with our Python code we open source is compile it into an executable so folks could use it with MATLAB code. We also have the vibration data toolbox, which is a nice GUI that will do all these calculations for you. It works great if you have one, maybe 2 or 3 profiles, but it's going to be a little cumbersome if you're trying to batch process something over time. You need your own, Python or MATLAB code. The other thing we have now is the enDAQ cloud, which will do all these calculations for an imported file, so you could track these various metrics over time. But admittedly, it's only doing that for data files that are generated from our devices. I plan, though, by the end of the year to open this up so any data file could be imported. And then you can monitor that over time. So I'm going to end this poll and share it. And as I expected, MATLAB is the end all be all, and I know that. And so we're going to look to help you all that use MATLAB. But there's a lot of folks too that like to do stuff in Excel. So I think that that compiled library I mentioned, as well as the cloud, can help get you a table view of these metrics so you can then play with it in Excel. And then I have a few resources for you. That blog that I published, again, goes deeper into all these topics. So check that out and subscribe. We'll generate some more content in this area. I know it's a popular one. How do you analyze your vibration data? So stick with us and we'll share that. But I think we have some questions, right, Tina?
Yes. So we get a question of these 12 metrics, which would be applicable in analyzing impact-related accelerations?
Oh, good. That's a good question. I'm glad that question came up. That's why I shared this shock response spectrum. If you're doing impacts, that's what I focus on, the shock response spectrum. Where is my peak in the shock response spectrum, as well as where's my frequency of that peak? That's what I would look at for impact transient events. Good question.
And then one of the other questions that we got was if you could recommend a software for calculating these.
Yeah, well, I think maybe that question came up before I got to the end. The vibration data toolbox is great. It's free. I'd encourage you to play around with that. The only downside with that is it really only works for a couple signals at a time. So if you want to do a bunch of different signals at once, you're really going to have to do that programmatically with Python or MATLAB code. So our team's going to be helping publish stuff in the next few months. So pay attention to help people with Python or MATLAB code, again, totally for free. And then the other option is that cloud software we have now. You import files, it will batch process them into those metrics. You could export that to Excel. And we're also even enabling paying customers in the cloud, because all that I just mentioned would be true for a free user, but paying customers in the cloud could customize how dashboards are generated and how these metrics are calculated. So you could really customize it. So I'm excited to release that. Well, that's a good question.
And we've got one more. If you have very low frequency data, generally below 0.5 hertz, how do you recommend thresholding between the low, medium, and high frequencies within that?
Yeah, so I mean, again, that's one of the nice things about the standard deviation calculation is that kind of it removes the low frequency content for us. It's an AC coupled way to calculate RMS. So I'd definitely encourage you to check that out. It kind of does a lot of the work for you. The other way you can do it is by applying a high pass filter to just get rid of that low frequency content. You can apply that high pass filter in post processing. You could also even just put in an RC filter in the analog chain, so you just get rid of the low frequency content before you even can calculate it. And then last but not least is once you have the power spectral density, in the frequency domain, in this view, you can also just kind of remove the low frequency content and just look at the higher frequency stuff. It's a good question.
So we are conducting some experiments. We put our acceleration sensor on speaker, which is connected to an amplifier and generating tones at specific frequency, like 10 hertz, 20 hertz, 30 hertz. When we checked acceleration peak, not getting exactly at the tone frequency, but getting near the value for peak velocity.
Yeah, not sure I fully follow the question, but so are they doing an FFT? I think, again, maybe they're saying, in the FFT they're not seeing what they'd expect, maybe, and that's kind of what I explained here is when you have a couple different tones, the FFT is not going to look right unless you can exactly get a complete number of cycles, which is impossible to do with real world data. So looking at the PSD would certainly help there. And maybe you could look at the peak in the PSD, which can be a helpful metric. And then, and that's the thing too, is I arbitrarily, well, it wasn't all that arbitrarily picked these three frequency ranges. Those are based on those industry standards I mentioned for imbalance, misalignment, and then real internal health of a system. But you could do the same thing for very defined frequency ranges and say, I know there's a tone at 200 hertz, so I want to measure RMS from 190 to 210, and that's the thing I'm going to track, as well as RMS from 80 to 120 for something around 100 hertz. That would be kind of what I'd do.
So working with acceleration G's from the sensor, how does this relate to static acceleration response of the structure?
The static acceleration response. Well, that might be, maybe they're asking, something about the shock response. There's a shock response spectrum. There's also a vibration response spectrum, which looks to quantify how a system, given natural frequencies and the input vibration or shock profile, respond. So maybe that's what they're getting at. I'm not quite sure.
Could you explain why you'd bin the data in 1 to 65, 65 to 300, and 300 to 6,000 hertz? I think you mentioned it is an industry standard. Why?
Yeah, it's because I'm trying to discretely define where is my fault condition. So again, when it's RMS levels are different for the lower frequency, less than 65 hertz, that tends to be related to imbalance. The middle frequency range, it tends to be related to looseness or misalignment, and the high frequency range is more at the heart of my system. But this is, again, it is somewhat industry standard, but you can do, once you have the power spectral density, you can define frequency ranges of interest that are maybe more useful to your specific application. Like if there's a resonance here, you just want to track the 10 hertz around your resonance, you can do that with the PSD. But that's why I use those three ones.
So another question is, could you please explain what is the difference between the random vibration PSD and the PSD you introduced here?
Not sure I understand that. So this is the PSD of the bearing data. I don't know if I understand that question. Sorry. I think there is no difference for the random when I'm using the bearing data. This PSD, if I plotted it on top of the one down here, the octave space, you'll see they're at the same levels. It almost looks like an average of them. Even if I were to plot these three discrete points in the G squared per hertz, so I'd have to normalize them to the bin width and square the terms, they will line up where you'd expect in this curve. I don't know if that answers the question.
We do have another one. Is there a particular method that is best for determining natural frequency?
Yeah, it would be once you have the relatively high resolution PSD and pulling out the peak. But again, it's hard with this. A lot of real world vibration profiles have many natural frequencies. As you can see here, there's clearly something going on in the 22 hertz, and there's something over here, in the higher frequency range. So that's where like sometimes I like actually looking at the 1/1 octave, and within each octave, looking at the peak in that range, if that makes sense. So that might be a way you can kind of track resonances for certain frequency ranges, because most real world vibrations have many resonances. But
there is another one that says, please explain the genesis behind classification of fault based on the frequency range.
Well, some of that I'm relying on industry standards, but some of that is somewhat, I guess, intuitive, where the low frequency is more related to, rigid body motion. If you picture a boat moving, that's only oscillating at a couple hertz, obviously, not even. And a big building is going to move from a earthquake at relatively low frequency ranges, right? But if you hit a piece of metal, that's like a metal beam, that's going to ring at a high frequency. And so that's a long way of me trying to say that the low frequency is tied to bigger things, which would be the boundary conditions. And then that's why imbalance in the motor is going to dominate the low frequency. When the high frequency starts to get kind of at the stiffer components, which are going to be the things inside your system, which is why it tends to be the health of your system and not influenced by your boat tilting or what have you.
All right. And the last one that we have here is, do we have any work or data from tunneling induced vibrations or from tunneling excavation using blasting?
I don't have them readily available. We certainly have a lot of mining customers that I can, there's been a few that have shared their data. So now when customers share their data with me, they tend to not tell me too much about where it came from other than it was mining. But we have some mining profiles that we could potentially share, but I don't have too much context. I don't know if that's helpful.
All right, so that concludes the questions that we've gotten.
Okay. Well, thank you all for attending, and this was great. Again, we're going to share this with you all. Check out the blog and subscribe with us, because we're going to generate a lot of this content to reinforce some of these topics in the few months ahead.
All right, so thank you everybody for attending today. We hope you found this webinar helpful and informative. If you have any other questions or think of something later, don't hesitate to contact us. We'll be sending out a recording of this webinar in the next few days, along with some helpful links, so be on the lookout for that. And again, from all of us at enDAQ, thank you so much for joining us today. Take care. Bye.
Thank you all. Bye now.